In Chapter 3, we begin discussing probability. In this chapter, we will learn key terms about probability, how to calculate probabilities, how to construct and interpret tables and diagrams, and this chapter will allow us to gain a deeper understanding of probability. We will use this chapter as the foundation of our probability knowledge as we move forward in this course, discussing techniques within inferential statistics. Probability allows us to connect the descriptive statistics that we learned in the last chapter with inferential statistics that we will be using over most of the rest of the semester. Let's start with some key terms so that we all know what we're talking about as we go through this chapter. First, experiment. An experiment is a planned activity carried out under controlled conditions. Next, we have outcome. An outcome is a particular result of an experiment. Sample space. A sample space is the set of all possible outcomes of an experiment. Next, we have event. Event is a subset of all of the outcomes of an experiment. It can contain any number of outcomes, from 0 to all of the outcomes in a sample space. Probability. Probability is a number between 0 and 1, inclusive, meaning it could equal 0 and it could equal 1, or anything between those two. This gives the likelihood that a specific event will occur. Equally likely means that each outcome of an experiment has the same probability. So these key terms will help us define what we are talking about as we move forward with probability. Let's discuss some basic probability rules that will help us as we move forward this chapter and beyond. First, probability is always between 0 and 1. When a probability equals 1, that means it cannot occur. So P of A equals 0 means the probability of event A is equal to 0, which means event A cannot occur. P of A equaling 1 means the probability of A equals 1. That means the event A must occur. Now, if event A was all of the outcomes in the sample space, then it would have to equal a probability of 1, because the sum of all of the probabilities in a sample space is equal to 1. A little bit more about probability. The probability of event A is equal to the number of ways event A can occur, divided by the number of outcomes in the sample space. A few other formulas that could be helpful to you. If you're looking for the probability of event A or B, that would be equal to the probability of event A plus the probability of event B minus the probability of event A and B occurring at the same time. The probability of A and B is equal to the probability of A given B occurred times the probability of B. This is sometimes rewritten solving for the probability of A given B. So we see that the probability of A given B equals the probability of A and B divided by the probability of B. And our last rule here is going to be the complement rule. So the probability of not A, so any outcome besides outcomes in event A, is going to be equal to 1 minus the probability of event A. Now these formulas will always work for us, but there are some special cases where we could modify these formulas to make them simpler. And those cases are when we have independent events or mutually exclusive events. Two events are independent events if the following are true. The probability of A and B equals the probability of A times the probability of B, which means the probability of A given B is equal to the probability of A, or that the probability of B given A is equal to the probability of B. Now, two events are mutually exclusive if the probability of A and B equals 0. So as we think about this, putting these into words, two events are independent events if the probability of one happening does not affect the probability of the other happening. Two events are mutually exclusive if the two events cannot happen at the same time. Let's look at a few examples. When drawing a card from a well-shuffled standard deck of 52 cards, what is the probability the card is a face card or a diamond? So we see the word or there, so we're going to use our or rule. So the probability of face card or diamond equals the probability of being a face card plus the probability of being a diamond minus the probability of both being a face card and a diamond. So thinking about our standard deck of cards, there are 3 face cards in every suit. There are 4 suits, that means there are 12 total face cards in the deck. Then we think about how many diamonds would we have. There are 13 total diamonds in a deck of cards. There are 13 of every suit. And then being both a face card and a diamond, that would be the face cards that are diamonds, and there's 3 of them. So the probability of being a face card is 12 over 52. 12 face cards in the deck, 52 total cards. Probability of being a diamond, there's 13 diamonds over the total 52 number of cards. And then the probability of being both a face card and a diamond, there are 3 face cards that are diamonds out of a total of 52 cards. So adding and then subtracting, we have 22 over 52, which simplifies to 11 over 26, or as a decimal rounded to 3 places, 0.423. Let's look at another example. Suppose that 35% of people own cats. If you pick 3 people at random, what is the probability that they both own a cat? Now, if you think about it, me owning a cat does not affect whether or not you will own a cat. So we would assume that these are independent events. So the probability of all 3 owning a cat would be the probability that person 1 owns a cat times the probability person 2 owns a cat and probability person 3 owns a cat. So the probability of each person owning a cat is 0.35. We always use our percents as decimals, and we always answer probability as a decimal, not a percent. So the probability that all 3 own a cat is 0.35 times 0.35 times 0.35, which will give us 0.043. Alright, so example 1, if you select a card from a well-shuffled standard deck of 52 cards, what is the probability that the card you select is a heart or a 5? We see that there's 13 hearts, there are 4 5s. The 5 of hearts is counted twice here. So we end up with the probability of being a heart or a 5 is 4 over 13. Suppose that 30% of people own goldfish. If you pick 2 people at random, what is the probability that they both own goldfish? Again, these would be independent events. So the probability both own goldfish is 30 over 100 times 30 over 100, which equals 9 over 100. So far, we have seen that the data has been fairly easy to work with when it comes to finding probabilities. It's not always the case, so sometimes we will want tree diagrams to help us in organizing the information to find probabilities. Each time that a tree branches off, the branches must account for all possibilities. The sum of the possibilities that each time our tree will branch off must be equal to 1. the best way to discuss tree diagrams is to actually look at an example. So let's look at an example and draw a tree diagram to organize our information about probabilities. At a plant, it is known that the probability a new worker will meet their quota given they attended the training program is 0.72, and the probability that an untrained worker meets the quota is 0.43. The probability a new worker attends training is 0.68. Draw a probability tree. So our point here that we start at before we branch off is starting the job. When we first start the job, we have a couple of possibilities. We can be trained or not be trained as a new worker. So we'll use T to represent training, and T with the horizontal bar over it to represent a not trained worker. Now, if you're trained, you can meet your quota or not meet your quota, and if you're untrained, you can meet your quota or not meet your quota. Now, we've got to talk about the probabilities and filling those in. So the probability that a new worker attends training is 0.68. So the probability that we go down this path towards training is 0.68. So what's the probability that we don't get trained? Well, since the branches have to add up to 1 and there's only 2 branches, 1 minus 0.68 gives us 0.32, which is the probability that a new worker is untrained. Now, we have to think about meeting quota and not meeting quota, both for trained workers and untrained workers. Reading back through our problem, we see that trained workers meet their quota with a probability of 0.72. So that means trained workers do not meet their quota with a probability of 0.28. Doing the same for untrained workers, the probability an untrained worker meets their quota is 0.43, and the probability that an untrained worker does not meet their quota is 0.57. Now, let's use this information as we actually find some probability. So use the probability tree to complete the following. What is the probability that a randomly selected worker meets their quota? Well, looking at our tree, there's 2 different places where a worker will meet their quota. If they're a trained worker that meets their quota, or if they're an untrained worker that meets their quota. So we see that we're really looking at the probability of being a trained worker and meeting quota, plus the probability of being an untrained worker and meeting quota, which is equal to the probability of being trained times the probability of meeting their quota given they were trained, plus the probability they were untrained times the probability they met their quota given they were untrained. Now these are all numbers that we know, so that means we have 0.68 times 0.72 plus 0.32 times 0.43, which gives us 0.6272. So approximately 0.627. Now, what is the probability that a randomly selected worker was trained given they met their quota? Now, this is slightly different than what we have already. So we're looking probability trained given they met quota. So it's the probability of being trained and meeting quota divided by the probability of meeting quota. And we've seen both of these before. We used in our last example the probability of trained and meeting quota. We saw that was 0.68 times 0.72, and we actually just found the probability of meeting the quota. So the probability of being trained given they met their quota is 0.68 times 0.72 divided by 0.6272, which gives us 0.781. Another way that we can organize our data is using a contingency table. The table organizes information that may be dependent or contingent on one another. Again, the best way to discuss contingency tables is to look at examples. So let's look at a few examples. we're going to find the following probabilities based on this contingency table. We see here that we have male and female students that got A's, B's, and C's. We can see the total number of students that got A's is 20, total number of students that got B's is 15, total number of students that got C's is 12. We have 28 total males and 19 total females. We're also able to see how many males got an A, got a B, or got a C, how many females got an A, got a B, or got a C. And in the bottom right corner, we're also able to see the total number of participants that we had in this experiment. So finding our probabilities, we want the probability that a randomly selected student gets an A. So that's the total number of students that got an A divided by the total number of students in our study, so 20 over 47, or 0.426. How about the probability that a randomly selected student got an A and they're a female? Well, there are 12 that are females that got A's, so 12 over 47 equals 0.255. How about probability that a student was a male or got a B, also stated as B or male? So looking at this, we have 15 total students that got B's, and we have 28 total students, and 13 of those were counted twice. So we have 15 plus 28 minus 13 should give us 30 out of the total 47, so that is 0.638. Now, how about the probability of C given they were a female? There's a few different ways that you could be going about this. You could be using your formula and saying probability of getting a C and being a female divided by the probability of being a female. You can also simplify it a little bit by looking at this. We are given that the student is a female. That narrows it down to the 19 females. So if we're given they're female, the denominator, our total, now becomes the total of just females. So there's 19 total females. Now how many got C's out of those females? Only 5 of them. So that's 5 over 19, giving us 0.263. Now this is the same exact answer that you would get if you used our formula, saying probability of C and female divided by probability of female. Now let's look for the probability of not male and A. So it's not a male that got an A. Now, from knowing our complement rule, we see it might be easier to do 1 minus the probability of being a male and getting an A. So what's the probability of being a male and getting an A? Well, there were 8 males that got A's out of the 47, so 1 minus 8 over 47 gives us 0.830. So giving a test to a group of students, the grades and gender are summarized below. If one student was chosen at random, find the probability the student got an A. So there's 14 that got an A out of the total 40. You would want to simplify this though. So simplifying it, you can divide both your numerator and denominator by 2, and you'd have 7 over 20. Giving a test to a group of students, the grades and gender are summarized below. If one student was chosen at random, find the probability that the student did not get a C. Well, you could be using the complement rule on this one. So there are 9 that did get a C, so 1 minus 9 over 40 gives us 31 over 40. Again, giving a test to a group of students, the grades and gender are summarized below. If one student was chosen at random, find the probability that the student was male and got a C. So male and C, that's 7. So 7 out of 40, 7 over 40. And again, giving a test to a group of students, the grades and gender are summarized below. If one student was chosen at random, find the probability that the student got an A given they are a female. So again, with a given, we're going to look in just the row or column for the given. Here we're given they are female, so we're looking in just the female row. So the total is 17. How many got an A? 10 of them got an A, so we have 10 over 17. Giving a test to a group of students, the grades and gender are summarized below. If one student was chosen at random, find the probability that the student was male or got a B. So there's 23 males, and there's 17 that got Bs. There's 12 that are males that got Bs. So that gives us 28 over 40, or 7 over 10. Giving a test to a group of students, the grades and gender are summarized below. If one student was chosen at random, find the probability the student was not a male that got an A. So not a male that got an A, using our complement rule, that's 1 minus the probability of being a male that got an A. There are 4 males that got an A out of the 40, so that's 1 minus 4 over 40, which is 36 over 40, so 9 over 10. Now, it is not always so easy to count the number of ways that events or outcomes might occur. Sometimes it's useful to have a tool for counting things quickly. So we have a few tools that we want to talk about here. First, permutations. Permutations are where order matters. This is where you pick and order k out of n total things. We see our notation here off to the right. And the formula is n factorial divided by n minus k factorial. Now a factorial is where we are multiplying n with every number below it. So n times n minus 1 times n minus 2 going all the way down. So for example, 5 factorial is 5 times 4 times 3 times 2 times 1. Now combinations, this is where order does not matter. We pick k out of n things. We see our notation and formula off to the right here. We notice the only difference between this formula and our last one is the denominator has k factorial in it. Our final counting rule here is the fundamental counting rule, and that says to count the number of ways that a combination of events can occur, events 1 through k, having n1, n2, n3 up to nk's ways that they can occur. The total number of ways would be n1 times n2 times n3 all the way up to times nk. Now, permutations and combinations can be found on the calculator. You would use the math button and scroll over to prob or PRB, and then find the appropriate notations. The fundamental counting rule is not on the calculator, and you will have to do this one by hand. Of course, we're going to practice with these. So let's assume that you are painting a house, and you have 3 choices for siding color, 4 choices for trim color, and 5 choices for door color. How many different color schemes are possible? Now we'll assume that none of the colors will clash and it will all look good. So this would be using the fundamental counting rule. There's 3 things we want to do. The first one can be done 3 ways, the second one 4 ways, the third one 5 ways. So we have 3 times 4 times 5 equals 60, so there's 60 possible color schemes. Now let's suppose you have a standard deck of cards. When drawing 5 cards, how many ways can you draw exactly 3 face cards? Now when drawing cards out of the deck, it does not matter the order that you drew them in, it's just the fact that you drew them. So we would be having a combination here. There are 12 face cards that we are trying to get. So 12 combination 3 equals 220. This is the number of ways to get 3 face cards. And then non-face cards, there are 40 of them. We're going to need 2 of them if we're drawing 5 cards and we're getting exactly 3 face cards. So 40 combination 2 is 780. So that's the number of ways to get 2 non-face cards. So putting our fundamental counting rule together with our combinations, we have 220 times 780, which gives us 171,600 ways to get exactly 3 face cards when drawing 5 cards. Now let's suppose that you are selecting 4 people to be president, vice president, secretary, and treasurer for a club. How many ways can these 4 positions be filled if there are 20 people in the club? Well, now there's a difference between president, vice president, secretary, and treasurer. So we would be using a permutation here. So 20 permute 4 would give us 116,280 ways that these 4 offices can be filled. Now, we can use these counting rules in conjunction with our probability rules to find probabilities when it's hard to count the number of ways that an event could occur. A poker hand consisting of 7 cards is dealt from a standard deck of 52 cards. Find the probability that the hand contains exactly 4 face cards. Well, now we're drawing 7 cards. We need 4 face cards. So there's 12 face cards, we want 4 of them, so we'd have a combination there. There's 40 non-face cards, we want 3 of them, another combination there. And then there's 52 total cards, we want 70 of them. So there's 12, choose 4, times 40, choose 3, number of ways of drawing these, exactly 4 face cards out of 7 cards. And then there's 52, choose 7 ways to draw 7 cards out of our deck of 52 cards. So this gives us 0.037 for a probability of drawing exactly 4 face cards out of 7. Now, what is the probability that if 15 letters are typed, no letters are repeated? So this means if we don't want any repetition, we're choosing 15 positions, all of them different, out of 26 different letters. So we have 26 permute 15, and the total number of ways that we could type this is 26 to the 15th. So the first letter, there's 26 ways, second letter, 26 ways, and so on. The denominator is using your fundamental counting rule, and the numerator is using your permutation rule. So we end up with the probability of typing 15 letters with no repeats. It's 0.006.